Welcome to our May 2025 installment of ENERCALC Office Hours. If you're counting, this is actually the 1 year anniversary of our monthly Office Hours program, so we're very excited about that. We're also very excited to let you guys know, if you didn't hear in the emails or in our LinkedIn announcements, that we are now offering a half-hour PDH certificate to Office Hours attendees. So we're very excited about that as well. If you've been with us before for office hours, you know that we have just a few quick housekeeping items to go through. If you're new with us this month, we have just a few things to take care of before we get started. So before we get going, I want to start with a quick sound check. If you direct your attention to the bottom menu of your Zoom window in your browser or your desktop app, you'll see the chat tool. We also have reaction emoji type tools down there. If you're able to hear me right now, just go ahead and throw a thumbs up emoji in the chat. Give us an okay, give us a reaction, something like that, and let us know that our sound quality is on the money. Perfect. Thank you guys for confirming that. And before we get on to the rest of our items, I also want to go ahead and do a quick sound check and a visual check for our primary speaker as well. So Mac is going to go ahead and share his screen at this time. And then once he does that, once again, if you can hear Mac's voice and you can see his screen, once he gets that all shared for us, then you can go ahead and give us, again, an okay, a thumbs up, what have you. So go ahead, Mac.
Hi, everyone, and welcome to another great session of the Office Hours program.
All right, good deal. So now that we have our tech checks out of the way, we are going to go ahead and disable the chat, and we'll move on to some introductions and get going with today's program. So most of you guys know my name is Seth Roseworm. I'm a senior structural engineer and a software developer here at ENERCALC, and our main presenter for the monthly ENERCALC Office Hours program is Mac Elterhony. Mac is a senior structural engineer here at ENERCALC, and he splits his time between providing technical training for ENERCALC customers, working with the ENERCALC engineering team on the specs and behavior of our software, and then also helping maintain a presence for ENERCALC at national and regional events. Mac is also the founder and managing principal of Elta Design Group, which is a specialty structural engineering firm based in Oklahoma City. And he's been an ENERCALC customer for about a decade, so he has a lot of great insight about the needs of our customers. So if you're new with us this month, there's a couple different things that Office Hours is all about to provide direct communication between us and our customers. Mainly, we showcase new features and updates from ENERCALC. We show optimized design workflows. We answer prepared questions that folks have sent to us ahead of time. And then we also do live Q&A with the audience at the end of every session. So if there's ever a question that's too involved or is going to require deep digging and research, that would be a better fit for our support team. They can always investigate your concerns, look under the hood, see what's going on with your question. As a minor point of order, you will notice everybody's microphones are muted just to make sure we don't get any echo or feedback during today's program. And as I mentioned, we do have open Q&A at the end of every session. If you want to submit a question for today's Q&A, you can use the Q&A dialog in the lower dashboard of your window. If you experience audio problems at any point during the session, you should be able to refresh your browser or rejoin the session. If you ever need to rewatch today's program or you want to share it with someone, all the recordings for our Office Hours sessions are posted to the Office Hours playlist on ENERCALC's YouTube channel. And with that, I will go ahead and hand it over to Mac to get going on our program for today.
Hello, everyone, and thank you, Seth, for the introduction. And again, welcome everybody to our monthly Office Hours program. As Seth said, I am Mac Eltarhouni, and I am excited to be presenting to you today about the pole footing embedded in soil module from the ENERCALC's library of diverse and extensive modules.
Just real quick, Mac, we don't have your screen share yet.
Okay, so
that's perfect.
Is it clear now?
Good to go.
All right. Okay. So without further ado, let's go ahead and start. So I'd like to start our session with a brief overview of the overall agenda for today. So we will be covering ENERCALC's latest build, and of course we have an announcement, surprise announcement, and next we have what's new in ENERCALC. And then we're going to get into the meat of our presentation today, which is the pole footing embedded in soil, which is based on the IBC implementation. And then we will cover how to register for office hours so you are notified of future events. And at the very end, of course, we will have a live Q&A. So please feel free to drop your questions in the Q&A form throughout the presentation. So first, we'd like to encourage you all to check your software to make sure that you are on the latest build of ENERCALC. So if you can take a minute and open your software, take a look at your current build, which is shown at the very top of your program to check where you're at. So we do monthly, we release monthly updates, and we want to make sure that our users are taking advantage of the newest features and program capabilities. We commonly receive, support questions from users where a user notes an issue, and typically, or a lot of the times, that issue has already been resolved, and they are just on an older build of ENERCALC. So always have the latest and greatest, always update to the newest to make sure that you are taking advantage of everything ENERCALC has to offer. To do that, all you need to do is just go here at the very top of the program. There is an update button, and if you just click on that, that will take you to this window right here where you can check for updates and launch the For Our Users page. So if you click on this one right here, that will take you to our website. And pretty much all you have to do is to click on this that says click to download the updater program, and that will pretty much update your ENERCALC to the latest and greatest. And if you would like the program to automatically check for updates at program startup, you can select this button right here. You can select this option right here. And a quick note here for all of our users who are on build 2023-0830 all the way to 2024-0228. So this, if you are in this range right here, the feature to notify you of the availability of new updates does not function properly. So if you are affected and if you are within this range, if you looked at your build and it's within this range, you need to do a manual update, but it's a one-time thing, and you can do that either from inside ENERCALC or through the website. So and you can do it easily again from inside ENERCALC just by clicking on this and doing it manually. So the current build of ENERCALC as of today is 2025-0507. This is the May 7th update that was released last week. So if you prefer to be notified of the latest ENERCALC updates by email, you can simply scan this QR code or go to this website, enercalc.com/update-emails. And all you need to do, just put your information here, and every time something new is released from ENERCALC, if there's any new build or new update, you will receive an email that says, hey, there's a new update, make sure you look into that and update to the latest and greatest. So some other people like to stay connected that way, and this is available to you. We are excited to offer the attendees of the Office Hours program, a 0.5 PDH, it's a half an hour PDH. And this is because the office hour sessions, we typically spend about 20 to 30 minutes, for announcements and live Q&A. So, but we do offer a solid, 30 minutes of technical content. Hence, we will be awarding half a PDH to reflect that technical portion, the guaranteed technical portion of the presentation. So in about a week or so, you will get an email with a link to download your PDH certificate for attending today's session. Now, if you have not been on the latest build of ENERCALC, or maybe you haven't had the chance to poke around and see what's new, I want to recap some of the main updates or kind of the highlights of the past 6 months in ENERCALC. So, of course, The first part that I want to discuss is the decoupling of the IBC and the ASCE editions. So some jurisdictions started mixing and matching design standards. So a jurisdiction will be on IBC 2015, but they want to use ASC 72022. So they're not matching anymore. And we used to have everything lumped up in one place, as you can see here. You know, the IBC 2018 that references the NDS 2018 or ACI 2014. So they used to be all in one place based on the IBC that references them. But now we went ahead and decoupled that, so this way you can mix and match to meet your jurisdictional requirement. So, and again, after decoupling, you can pretty much use whatever combination that works for you. This, of course, gives you the flexibility that you need to move forward with your calculation packages. The second update is the addition of the new ASCE 722 modules. You might have noticed that we started adding 3 new tabs here. The seismic and wind loads and the other loads. So the first tab again is the seismic, and that's where you will have all of the seismic modules, or the seismic calculations, base shear or wall anchorage, and we have here seismic demands and non-structural components. Moving on to the next tab, you have the wind loads, where we added calculations for the ASC 72022. And we used to have these 3 right here, which is chapter 27, 28, and we had a calculator for wind enclosure. And as of last week, which is the latest and greatest build, we just added the ASCE 722 wind forces per chapter 30, and that is the component and cladding chapter. So you can get your pressures using this module now, and this is publicly available as of last week. And of course, the last tab we have here is the other loads, and that's the one that houses some of the other miscellaneous modules that we have that relate to loads and forces, such as snow loads and live load reduction, and everything that kind of doesn't exactly fall under wind loads and seismic loads will be housed under this tab as we go. Next is native load linking within ENERCALC, and this has been an exciting feature with rapid development. So for those who do not know, load linking is an ENERCALC native feature that gives you or the users the ability to automatically link reactions from one calculation to another. And the ability to change something in one calculation in one member, and having all of those effects, all of those reactions trickle down to all of the supporting members or the downstream members. So currently, ENERCALC native load linking is available in steel beams, wood beams, steel columns, and wood columns, with more integration into other modules underway. So again, this is rapidly growing, and we keep on adding many more modules as we go. To showcase load linking in a way that relates to daily applications, we want to go through an example of how load linking can save you time and minimize errors. So in this example, we want to use ENERCALC load linking to design wood and steel columns by linking reactions from various beams as shown on this sketch right here. So you can see here on the left-hand side, we have a wood column, and on the right-hand side, we have a steel column right here. So we'll be kind of working on this a little bit to get you more familiar with how to use load linking. So we can easily do this by following a few simple steps, and the process is extremely intuitive. So we have a wood column on the left side, and we have the steel column on the right side, and so we're going to go ahead and start with this wood column right here. So before we start with linking loads, we actually have to create calculations for the beams. So we have, for example, for the wood column, we have wood beam 1, we have wood beam 2, and we have steel beam 1. So the first thing that we have to do, we have to create calculations, beam calculations for these 3 beams. This is a typical process that all of ENERCALC users are familiar with and know how to do. So for the purpose of this example, we will not walk through the process of how to create a beam calculation. But just to give you a flow chart, the first thing you need to do, you need to be able to create these 3 different calculations in ENERCALC. Once the beam calculations have been created, they of course will appear in ENERCALC, on the project manager folder or structure. It will show these 3 beams, as you can see in the snippet right here. So you have steel beam 1, wood beam 1, and wood beam 2. So they will be created. And once they are created, we are ready to move on to step number 2. Step number 2 is to create a calculation for your wood column. So the process is simple. To do so, you just follow the process by clicking on the add button, and then you'll have this menu, the module selection. You click on columns, and then you click on wood columns so you can create that calculation. Once you create that calculation, you can set it up like you always have done. You set it up like normal. This means all of your standard input information, such as column height and restraint conditions, wood species, slenderness, K-factor for each direction, and all of the stuff that you have to do in order to create a calculation. So for the purpose of this example, we will not go through the process of how to create a wood column calculation. We already have an office hour session that covered wood columns, and that can be accessed on our website. So you are, the purpose of this is that you already know how to do that. So now we move on to the next step. Once a wood column calculation has been created and set up, now we are ready to start linking the reactions from the 3 highlighted beams right here. So we're working on the left-hand side. So those are the beams that we want to link. And to do so, as you know, you will get these many tabs that you have whenever you have a wood column, and there is this tab that says linked loads. This is different from loads. Loads, this tab right here, that's just for applying loads manually. Linked loads, that means you are bringing loads or reactions from an already created calculation. So once you click on this tab, the linked loads tab, you will get this interface right here. So you will see a list of all of the calculations that we already created on the left-hand side. And you can see here it says select a beam calculation. We have steel beam 1, wood beam 1, and wood beam 2. So for the purpose of this, the first item we want, or the first reaction we want to link, is from wood beam 1. It's this reaction right here. So we click on wood beam 1. Once you click on that, the 2D sketch on the right-hand side will dynamically change to reflect and show the free body diagram of the beam that you selected. And this is, of course, a great visual confirmation tool to make sure that you're indeed looking at the correct, or you're grabbing the correct beam. Now, next, once we have the wood beam selected, we need to pick the reaction that we're interested in. So is it the reaction from support 1, or is it the reaction from support 2? So in this case, we're interested in support 1. So you click on support 1. Once you click on that, then you move on to this middle section of the window, and that section right here talks about how that load or the reaction is meant to be applied on the column. So you have here the ability to have a multiplier if you want that reaction to be multiplied twice, for example, 3 times, whatever. And then you have here load eccentricity, and you can work on the eccentricity measurement to be from the center of the column or measured from the edge of the column. And of course, you can put the load at the top of the column, or you can specify at a specific height, maybe at midspan or at 3 feet from the base or what have you. So with that being said, we have this right here. This load is applied with eccentricity, and that eccentricity is 3 inches in the positive y direction. So that's why this is the y direction, and we're putting this as a positive 3, and that will model the load all the way out here. And lastly, the last table we have, this is a table that summarizes all of the reactions that have been linked. It gives you information about the source of the reaction, which in this case is wood beam 1, and it gives you some information about the placement and where it's at, and then it tells you what that load is. You know, this is a dead load, this is a live load, or roof live, and if there's anything else, it will show it right here, so you have a good idea of what's going on with your beam. The next step we want to do is link this reaction, because now we're done with wood beam 1 and we're ready to link the reaction from steel beam 1. The process is exactly the same. You click on steel beam 1, and of course that will update the 2D sketch, the free body diagram on the right hand side. You pick the support that you want, and you pick the eccentricity. So in this case, this is in the negative y direction. So that's why we apply it as -3 or -3 in the y direction. That's the eccentricity. Everything else is pretty much good to go. So you add it, and you can check it here in this summary of loads or summary table below. And the last piece of the puzzle is the reaction from wood beam 2. The exact same process. You pick it, you pick the support, and this one is actually, it has eccentricity in the positive x direction. So this actually will induce some bending in the minor axis or the weak axis of this particular column. So we have that as 2 inches. So we're applying it as 2 inches from the center of the column. And again, it gets added and it's summarized in this table. So all looks good to me. And once everything is confirmed and looks good to you, you're ready to move on. So once you apply all of this load, or once you link all of these reactions, your column is ready to go. And if you actually click on the 2D tab within the wood column module, you'll be able to see a 2D representation of the cross section. And you can see here that it shows the first load right here, the second load right here, and the third load right here. So this gives you just additional visual confirmation of the load to make sure that you are applying everything the way that you want to apply it. So now that all of these beams are connected to the column, you have a dynamic live chain between these calculations, these beam calculations, and this column calculation. So if the reaction from wood beam 1, for example, if this reaction changes, then this change will carry over to the wood column calculation automatically without ever having to manually input or manually transcribe these reactions in the future, and eliminating all chances of errors. So now that we're done with the wood column, we're ready to move on to the next step, which is step 3 in this particular flow. We need to do the same thing for the steel column. So we will create a new steel column calculation to link the 3 beams that are highlighted right here in this sketch, which is wood beam 1, steel beam 1, and wood beam 2. And to do so, we follow the same typical process. We already have the beams already created, the beam calculation. So all we have to do is just create a new column calculation by clicking on the add button, then clicking on columns, and of course, clicking on the steel column module. And once a steel column calculation is set up, we are ready to link the reactions from the 3 highlighted beams. So again, you click on the linked loads tab, and it's the exact same process. You start with wood beam 1, that's what we're linking. You pick the reaction, and now we want to put, 3.5 inches worth of eccentricity. So we put it right here, and you apply the load. That's in the positive Y direction, 3.5 inches. Next, you do the same thing for steel beam. So you pick it up from here, you pick the support that you want to grab the reaction from, and now it's negative 3.5 inches since it's in the negative Y direction. And lastly, we have wood beam 2, and we can pick the reaction yet again, and we can put it as a negative 3.5 inches in the X direction. So that's why it's shown right here. Now, additionally, what this column has that's different from the wood column, this column has an additional dead load of 3 kips that's placed on top of this column. This load is not linked from anywhere. This load is a manually applied load. Hence, we have to click on the Loads tab, and then you click on Axial Loads, and you follow the standard process that we've always used to apply loads. You just put right here, that's your dead load, is 3 kips. We don't have any eccentricity. We're saying that this is concentrically applied. So we put that right here. And of course, we want that to be applied at the top of the column. So that'll be applied at the top of the column. And just like that, you have linked all the 3 reactions from the 3 beams, and you added a point load to this column. And for one final visual confirmation, we click on the 2D tab inside ENERCALC to see what the cross-section looks like. And you can see right here, the cross-section shows this load right here, and it shows a load on the left-hand side and on the bottom, and it shows a load right here in the center. Now, it's important for you to note that linked loads are going to have a different color than manually applied loads. So if you look at this one right here, the linked loads are shown in blue, and anything you apply manually is going to show in red. This is extremely useful whenever you're looking at a cross-section or you're looking at the applied loads visually. You will be able to immediately tell if a particular load is linked or a reaction is linked or manually applied. That would help you address if you have any discrepancies. So now that all the beam reactions have been linked to the columns, you can see that the columns display a new badge indicating that they are part of a chain. You see that right here. So that's the wood columns and then the steel columns. So the columns show the badge because they are dependent on the results from a preceding beam calculation. So these guys here have the badge because they are dependent on something from here. However, the beams do not have a badge because they are not dependent on any other preceding calculation. So when I see a link in wood column, I know that the wood column is grabbing a reaction from somewhere. If you look at the wood beam and you don't see anything, then I know the wood beam is not grabbing a reaction from anything. Now, the wood beam could be part of a downstream calculation, but we know this is not dependent on anything preceding it. Nothing, it's not linking any reaction into it. So that's why they don't have a badge, and these 2 columns, have a badge. There are 3 badges, and each badge represents a message. So for example, green, this green badge right here, it means that the reactions that we linked into the column, for example, they're up to date, while orange and red will indicate that the reactions linked are not really up to date and some work that needs to happen. The yellow indicates that the reaction from the preceding calculation has changed, so you need to change the column. And this one's saying that there are multiple layers of updates that need to happen. Maybe beam 1 sits on beam 2 and beam 2 sits on the column. Beam 1 and beam 2 have changed. The column is going to be red. So either way, whenever you see red or orange, definitely you know that your reactions that you have linked are no longer up to date. So for example, if I open the calc for steel beam 1, this one right here, if I open the calculation for steel beam 1 and I change the span, currently the span is 8.5 feet. If I change the span to 6 feet, then that change will change the reaction. And as soon as I click on save and close and, get out of this calculation, the column will display this yellow badge saying that, oh, the reaction that we're grabbing has changed. You need to update these columns by, updating them by triggering a recalc. So that's kind of what the yellow badge would mean in this instance. And once we do a bulk recalc, for example, that will bring the columns back into compliance from a load path perspective. So you can trigger a bulk recalc by simply clicking on this option that you have at the top. This button right here, it's called Recalculate Linked Loads. And once you click on it, ENERCALC will perform the calculations following the proper load path, and it will update all of the reactions that are referenced, not just in one, but in all of your calculations, meaning that both of the wood column and the steel column, both of the columns will actually get updated, because this will go through all of the calculations, go through all of the load paths, and make sure that everything is up to date, and all of calculations that are out of compliance or are not updated are brought back into compliance with the latest and greatest reaction. So overall, load linking is a powerful tool that allows the engineers to create well-connected chain of calculations, and it minimizes the risk of transcription errors. We do have here on our YouTube page, we have a whole playlist that goes through the whole process step by step and makes sure that you understand every little tool we have and every little note or every little warning. We also created additional tutorial and playlists on our YouTube channel. Most recently, we have the composite beam module as well as the soldier pile retaining wall module. And of course, we're going to continue working on adding more playlists, tutorial playlists. The next item we have here on the agenda is the update to the IBC 2024. So now IBC 2024 is incorporated in ENERCALC. And if you ever want to use that, all you have to do is click on General, then go to Building Code Information from the Project Manager and select IBC 2024. Alternatively, you can just click on this button at the very top that says Building Code and Load Combinations, and it will bring you to the same thing, and you can click on the IBC 2024. Keep in mind, this will only change the governing code in the one ENERCALC file that you're working on. If you want to change the default values for all of your future projects, then all you have to do is click on Settings, and then click on Default Governing Code and ASCE 7 Edition. And then from here, you can pick the code that you want. In this case, we want IBC 2024. And you can pick the ASCE that you want to use. And then you click OK or Select. That will make sure that all of your future projects will have IBC 2024 as the default starting code. Another item we want to highlight is ENERCALC for Revit. ENERCALC for Revit is a Revit plugin that allows you to design structural members fully within Revit without having to export information to any other calculation software. You can see that all of the design work, all of the work that you're doing is within Revit right here. All of your commands, all of your controls, you can control what your K value is, all of that happening completely inside Revit as a simple point and click workflow that allows you, of course, to design these members completely in a fraction of the time and completely accurately. So all you have to do is just really click on one member, and you'll start with the design process. And this right here is more of a guided prompts that will help you walk through everything you need to do, from determining your tributary width to what your supports and all of that stuff. So currently, ENERCALC for Revit supports the design of steel beams, steel composite beams, wood beams, steel columns, and foundations. So you have a full gravity load path with more development underway. And of course, while we're on this topic, Revit 2026 was released in April 2025. So, and we're excited to say that ENERCALC for Revit now provides support for Revit 2026. So this way, if you have a project that's in Revit 2026, we make sure that ENERCALC is never the bottleneck of your workflow. So we try our best to match the release date, within few days max, from when Revit releases the new version, where we release our ENERCALC for Revit support for that, and for compatibility wise. Another great update is the ability to export tabular detailed results from ENERCALC to a CSV file. So this is really useful for many engineers, because a lot of engineers like to post-process some of the results outside of ENERCALC. So all you need to do this, just go to the results that you're interested in, maybe, detailed results, go to the ASD Shear moments, and, this gives you all kinds of intermediate values, such as KL over R, or, the F critical. You get all kinds of information. You just right click and you say save to CSV, and that will save all of that information for you to a CSV file to your machine. And you can export, these CSV or the results into a CSV file in most of our modules, including columns, beams, slender and shear walls, foundations. So this feature covers everything except for the loads and forces modules, and that is currently underway, but everything else is included. And now we also have this new update where if you go to ENERCALC, to your update tab right here, you can subscribe to the email that tells you exactly what changed in every new update. So that's kind of the release notes. You can simply just click on the update button and then click on this, and you can just click on subscribe, and that will allow you to subscribe. For your information right here, this is what the email that you would get looks like. So for example, this is the latest and greatest build. You get the highlights, or the major highlight of what changed. Like, for example, we added the component cladding module. We added a few things here. And then you can see here at the bottom, it says we've made a total of 25 total enhancements this month. And if you click on this link, you'll get a full list. Now, the list is actually a little bit more detailed. So for example, it says wood beam. This tells you that we clarified that the repetitive member factor does not apply to glulam members. So that kind of did a bug fix here and kind of made sure that everybody understand what's happening. This one right here, it says that now we have the CSV option that we just talked about. We have incorporated in the analysis and the miscellaneous modules. So you can get a case number, and you get a lot more details on what changed in case you have something that you specifically want to follow. So moving on to the focus of our session today, which is the design of pole footings embedded in soil by following the IBC method to determine the minimum requirement, or the minimum required embedment to support lateral loads. A quick overview of the capabilities of this module is that it analyzes and designs based on the IBC 2021 section 1807.3, and this does it also for IBC 2018 and the others, but the example today revolves around IBC 2021. Next, what it also does is that you can apply axial loads, concentrated lateral loads. You can apply distributed lateral loads and concentrated moments. Also, it gives you an option for non-constrained, as well as an option for constrained conditions, so you can design based on your condition. And it allows you to manually input the embedment depth, or if you want, ENERCALC can auto-calculate minimum depth for you. And lastly, of course, just the same case with all of our modules almost, is that you will have dynamic 2D sketches and 3D sketch for visual confirmation, and these sketches are reflective of your unique calculation. They're not just random generic sketches. So in today's example, we want to determine the minimum required embedment for a pole footing in soil. So what we have a circular footing. The diameter is 30 inches. Top of footing is considered constrained. The allowable lateral passive pressure is 100 psf per foot of depth of foundation. Maximum lateral pressure limit is 3,000 psf. Lateral point load, which is from wind, 1.0 wind, that is 3 kips. So that is applied lateral load here. And vertical dead load, which is again 1.0 dead, that is going to be 2 kips that's applied on top of the pole. And we have here the lateral load is applied at 5 feet above the foundation or above the footing. And of course, we have here allowable end bearing capacity of 1,500. So to start a new pole footing calculation, we follow the same familiar process. We click on the Add button, then Foundations, and then click on the pole footing embedded in soil. Once you do this, we will just work our way from left to right. This is a simple module. We work our way from left to right, starting with the General tab. So we give our calculation a name. I'm calling this Constrained Pole Footing. We then move on, and based on our example, we have a circular footing that is 30 inches in diameter. So we input that information here. You click on circular and you put the 30 inches diameter. If you have a square footing, then it'll ask you for the width, and it will carry on with the calculations accordingly. Now, this option right here that says restraint at ground surface exists. The IBC allows us the design of footing as either constrained or not constrained. So you can see here that there are 2 formulas, and those are the sections from IBC 2021. This is the formula that needs to be used for non-constrained, and this is the formula to be used for constrained. So since our example is constrained, so we're going to check this box, and that will tell the software to use the proper equation. Now, moving on to the next part, ENERCALC has 2 operational modes. It can determine the lateral pressure for a given depth, and that's if you click on this option right here, it's called Find Lateral Pressure for a Given Depth. So if you click on it, then the user will be expected to input the depth that they need to examine. If you're looking at 7 feet, 8 feet, whatever guess you want to take. So, or maybe you have something existing that you want to check. So you're not really designing. You want to do some analysis and examine if it works or not. So by clicking on this option, you get to input your own embedment depth. In this case, I just chose 6.75, and the calculations were run based on that. However, in our example, we want to determine the minimum required embedment for the footing to work. That means we need to move on and click on the calculate minimum depth. So what happens here is that ENERCALC is going to iterate until it finds the exact minimum depth needed. Hence, this is obviously a process that's trial and error a little bit. So for our case, we just want to click on this and let ENERCALC do that heavy lifting. And at the bottom of the page, the user needs to input the allowable lateral pressure. And this was given in the example for us as 100 psf per foot. So typically this can be obtained either from a G-technical report or from the IBC presumptive values per table 1806.2. Again, all of these references are IBC 2021. So, but everything is going to be in chapter 18. So, for example, if we have clay soil, you have 100 psf for lateral bearing pressure, and we have 1,500 psf for vertical allowable bearing pressure, which those are the same values that were provided in the example for us. So that's kind of this part right here. That's the 100. And then, of course, the last piece of the puzzle here is the maximum lateral pressure limit that we don't want to exceed. That's the maximum. And that is 3,000, again, given in the example. And you can see right here, it says enter 0 for no limit. So if you don't have a cap, if you don't have a maximum lateral pressure that is that you're capping the soil capacity at, then you can just put 0, and this limit will be ignored. So next we jump into the applied loads tab. From the example, we have a 3 kips. This is the lateral concentrated loads. We have 3 kips wind, so we put it here, and we have it at 5 feet above surface. We also have axial load of 2 kips. It's worth noting here that you can apply moments directly, or what you can also do is that you have the ability to apply up to 3 different lateral loads, and these don't have to be fully uniform. They could be partially uniform loads. So you can have a load from from 0 all the way to the top, which is 5 feet in our example, or you can have a load maybe from 0 to 2 feet, and then another load from 2 to 5 or whatever. So you can apply here partially uniform loads, and the calculations will be performed properly. We don't have any of this in our example, so we are ready to move forward. Of course, the last piece here is, or last tab is the load combinations. So I want to use IBC 2021 load combination, so you can select that from here. And then the rest of this is just your standard ASD combinations. We're going to keep everything as is. And now it's finally the time to evaluate the results. So if you click on calculations, you'll be able to see the controlling combination, which is D plus 0.6 wind, which again, D is 0 from a lateral perspective. So it's just 0.6 wind. So 3 times 0.6, that's 1.8 kips. That's the applied load, and that's the moment that it generates on the footing. And this did the calculation that came up with a minimum required embedment depth of 5.37375. On this right-hand side here, you get some more information, such as the actual pressure versus the allowable soil pressure. And you'll get some information here regarding the surface restraining force. And right here, we have the footing base area, which is based on the 30-inch diameter, and it provides you here with the maximum applied axial soil pressure, which is really the axial load, the 2 kips that we have, divided by the area. Now the demand is 0.407, and of course we know the soil capacity was 1500 PSF, or 1.5 KSF. So this, from an end bearing perspective, from soil bearing perspective, is good to go. And also for visual inspections, you can click on the 2D tab. And this is right here. So you have 2D tab and 3D tab. Every time we talk about the 2D and 3D tabs are typically on the right-hand side by the summary of calculation. So if you click on the 2D tab, you'll see a sketch of the assembly. And you can see here the embedment is 5 foot 4.5 inches. And we have here the height of this is 5 feet. And you can see more information such as surface lateral restraint. And you have here the point load. That's a good visual confirmation. And lastly, 3D visual confirmation is the best, because you can see your actual load, 3 kips wind, 2 kips dead, and 5 feet and 5.38. This just rounds up a little bit. So everything looks good. Everyone is happy. And to wrap this up, I want to just have a quick back check with a hand calculation. This is the equation that we need to use. And of course, we can, I went through the process here where, we have the point load is 3 times 0.6, which is 1.8. The width of the footing is 30 inches, 2.5 feet, and the height is 5 feet, and S3 is the depth, which is, I'm assuming, 5.35 multiplied by 100, which is 100 psf for lateral pressure. That gives you 535. The way it works is that you assume a depth, you calculate S3, you then put it in this equation, and if the calculated D turns out to be equal to the assumed depth, then that means the results have converged and you are pretty much, coming up with the minimum embedment. If you actually do 5.35 and iterate and do all that stuff, you will be able to actually converge here with the D calculation at 5.35. So we're good to go. And the last couple things here I want to mention is that ENERCALC calculate this minimum embedment to be 5.375, and I calculated it to be 5.35. And the reason for this is that ENERCALC rounds up the final number. And this is actually taken directly from our user manual. It says, when the program finds an embedment depth for which the actual pressure is lower than the allowable pressure, it rounds the embedment depth up slightly and reports that value. So this is done by design, but it's almost, a very small amount of rounding. Last thing to note about this is that IBC has some limitations and some additional information. The two items that I want to note is this item number 2 that says that this cannot be used to support, to provide lateral support for structural or non-structural materials such as plaster, masonry, concrete, etc., unless bracing is provided that develops the limited deflection required. So that's, you'd have to provide additional bracing to control deflection. And this one right here, increase for poles, they're saying that, for flag poles and signs, if they are not adversely affected by half an inch movement or motion at the ground surface, then you can actually multiply the capacity or the lateral bearing pressure. You can multiply it by 2 or 2 times the tabular value, and they're talking here about the presumptive table values, and that means instead of using 100 you could use 200. So if that's something that applies to you, you can go ahead and apply 200 in ENERCALC instead of 100. That would be something that you would have to evaluate and use the increase if your case allows for it. So lastly, I just want to make sure that, before we dive into the Q&A, I want to encourage everybody to register for office hours, just to make sure that you're taking advantage of this. You can just go to enercalc.com/office hours, or you can go to our regular website, click on for our users, get help, and then office hours button right here. And of course, that'll take you to put your information and you can register. Keep in mind, always at the bottom here of this page, you can see when our next session is, the Zoom link to join, and the ability to add that to your calendar. And at that same website, we get this question quite a bit. So at that same website, which is enercalc.com/office hours, you can find all of the unedited recordings of the previous sessions. All you need to do is just scroll down a little bit and you will find all of them. The last one we did from April, that was the miscellaneous modules session that covered steel base plate and bolt group analysis, and that was held on April 9th. So we always, including this session in a few days, will be updated to our website. So we always have these updated to our website. And again, I want to remind everyone that you will receive an email with a link to your PDF certificate, for PDH, within a week or so. So stay tuned on your website and your email. And if you don't get it within a week or 10 days, feel free to reach back to us. So with that, we are ready to open this up to the Q&A. If you have any questions.
All right, let's get into some Q&A. So first question, could you add a calculation to determine the maximum moment in the pole? This would occur at the point of zero shear in the embedment. So this is kind of an interesting question. And Mac, feel free to add any thoughts you have. But like Mac said, This particular module is a direct implementation of the IBC equations for posts and poles, embedded posts and poles, which is IBC 1807.3. The IBC derived equations don't explicitly include any background information about the specific pressure distribution that's being used. And so it's not really feasible to directly calculate a shear and moment diagram for the pole without knowing what soil distribution um,
Absolutely.
the IBC equations assume. So you could go through that process by assuming your own distribution. It's just not entirely clear from the IBC provisions how your assumptions would stack up against the calculations from the IBC. Go ahead, Mac, if you have more thoughts on that.
No, absolutely nailed this on the head. And again, this is just an implementation of the IBC, and the IBC doesn't tell you, their assumptions fully or how to do such a thing. And in my experience, whenever I use, whenever we do some design work for peers, or if we have, moment applied on peers, for example, we would have to know more, not just from a distribution perspective, but also, the layers of the soil. We get a lot more information from the GTEC report to tell us about every soil and its lateral bearing capacity and the depth of that particular layer. So there is a lot more that goes into this for us to be able to provide more insight on that moment diagram.
Yeah, for sure. And that's one of the reasons that it's good that Mac touched on the limitations of the module and the limitations in the building code itself. We want to be clear that this is not necessarily an open ended soil structure interaction type analysis. This is a more code dictated approach. Now, there's a related question similar to what was just asked, and that would be having to do with the restraint force. You would be correct in saying, hey, in order to get restraint force for the restrained condition, you would need a soil distribution in order to get a horizontal summation of forces and figure out the restraint force at the pavement level. And so I believe we have documentation that specifically indicates we are presuming a triangular distribution to at least give the user a frame of reference for what that restraint force might be. But you do
Absolutely, yeah,
have to
that
have an
part.
assumption, and you do have to be clear about the fact that the building code doesn't specifically state, how that presumption of a triangular distribution would stack up.
Yeah, absolutely. Yeah, again, this is absolutely right, because we make an assumption, but that is outside the scope of the IBC implementation. That's not part of the IBC implementation, and we make that assumption, and we just to give you again just an idea, and it is a triangular distribution that we assume, but we do not. It's not something that the IBC supports.
Yeah. All right. Question from Bill. How can I submit feedback on an error I've found within ENERCALC when printing wood shear walls in the project manager? So we always, always, always would love to hear from you if you have any kind of if you have a bug report, if you have a question. We always want to encourage you to reach out. Support@enercalc.com is where you want to send that question. That'll go directly to our engineering team. Max sees those questions. I see those questions. Our entire structural engineering team dives into those, tackles those, and we'll replicate if there's a bug, pass that to the development team, and then let you know when there's an update. And we always just want to reiterate, everyone on our structural engineering team is US based, licensed structural engineers, all of whom spent a decade at least, or more than a decade in most cases, designing building structures as an ENERCALC customer before joining the ENERCALC team. And so, yeah, absolutely reach out with those questions. Next question. Did I miss that all the beams are hanging from the face of the column? I believe this question was in reference to our load linking walkthrough. So, and I think
Yes.
Mac dove into some detail after this question was posed about those relationships. He did the eccentricity from faces. He did all of those relationships. Hopefully that answered that question. But Mac, go ahead if you wanted to add any more clarity on
Yes,
that.
in a nutshell, yes. All of these are the way that I have modeled them, and the way that I worked out the example is that they're not resting on top of the column. They're all from the face. However, in what's important to know is that this is just an example. If everything sits on top of the column, then you don't have to provide any eccentricity. You can just put that at 0, and the load will just be applied instead of on the outside. It'll just be applied on the center of the column. So pretty much this is just to show you the possibility that you can do something with eccentricity, but you can do whatever you'd like.
Yeah, and one of the cool things about that interface is just like in your regular column load interface, where you've always been able to place those eccentricities either about the face of the column or from the centroid of the column. You have that flexibility where you can specify, oh, I like in the case of a steel connection, for example, I know how far my bolt line is from the face of the column, or in a bearing situation where the centroid is the most important thing. You have the flexibility to specify either way. All
Yeah,
right.
and the way that we did, load linking for columns, we wanted it to be reminiscent of the column module. So if you see here loaded eccentricity X and Y, and then measured from this, all of that, if you click on your regular loads tab, you see the exact same thing. Load eccentricity, this measured from, the edge of the column. So we're trying to kind of have a similar theme. So this way you're not just looking at this for the first time. This is reminiscent of the same load application method that we've always used in for example, in the steel column or the wood column or all of our column modules.
All right, next question. Are we able to complete composite steel and concrete beam design for bridge analysis with an ENERCALC for Revit interaction currently, load linking, etc., or just by itself as long as we take care of factored loads from AASHTO? So I want to kind of peel back the layers here. There's several things to address here. First of all, I think all of our experienced users know this, but just to be clear, we don't support at this time AASHTO design codes for actual material capacity checks. So if you're doing steel, you're doing concrete, etc., absolutely be aware that we're using ACI for concrete and AISC for steel design checks. However, if you're doing analysis, you need shear and moment, you need reactions, you need deflection, those kind of things. You absolutely can synthesize your own AASHTO-like load combinations and do those analyses. So kind of want to get that out of the way first. And then when it comes to load linking for steel composite, you don't have steel composite natively for load linking in ENERCALC right now. However, you can do load linking, complete load linking for steel composite floor framing systems inside ENERCALC for Revit. So if you have a Revit floor framing system with steel composite beams, you can seamlessly link those reaction forces from a composite beam to a composite girder to a composite transfer girder. You can do that seamlessly inside your Revit model using ENERCALC for Revit behaviors. Now, that's not true of concrete beam at this time. ENERCALC for Revit doesn't yet have a concrete beam integration. If that's something you're interested in seeing, be sure to reach out to the support team, support@enercalc.com. If you're doing workflows where a concrete ENERCALC for Revit integration would be useful, be sure to let us know about that. Let me know if that covered your question. Hopefully it did. All right, next question. And this is more like a feature request from Joe. Maybe add a button to column module to change the material so the existing input can be used for additional column types. And that's basically referring to the toggle button that you have in the beam module where you can establish the beam calculation and then toggle it from a steel beam to a wood beam to a concrete beam. That would go under the heading of a feature request. Obviously the engineering team attends these sessions and they're listening and taking note of this, but we always want you to reach out with those so that we can track how many customers are asking for those kind of things. So again, if you have a feature request like that, go ahead and email that to us at support@enercalc.com, and that can go to the engineering team, because that's kind of how we track and gauge the level of demand for those things. All right, next question. How do you interpret D equals depth of embedment in earth in feet, but not over 12 feet for the purpose of computing lateral pressure? Does this mean the maximum depth that can be utilized for this formula is 12 feet, or that the maximum lateral pressure is capped at 12 times the allowable passive per foot?
The maximum
Mac,
that can be utilized.
I'm not entirely sure if this is in
Yes,
reference to something you
that's
covered or if this is in reference to a limitation in the building code. Go ahead.
he is talking about the
Yes.
12-foot limit per the IBC. And the way we see it in the IBC is that they say that you cannot take for lateral pressure, or from a capacity perspective, you cannot take more than 12 feet multiplied by the 12 feet multiplied by the passive pressure. So if your passive pressure or your lateral pressure is 100 pounds and you have a pole footing that's going down 15 feet, you can only take 12 feet multiplied by that 100. So that puts the cap there on you. So it doesn't matter if like as far as the IBC goes, it doesn't matter how deep you need to go. They cannot take more than 12 feet. So let me take one important thing here. If you're doing the restraint at ground surface, if you have that already included, then that means for the S calculation, I want to bring this up here. This is a really good question that really highlights a contentious point sometimes. The equation right here that we have for the constraint, S3 is the full depth. So we have 10 feet, 12 feet, whatever that number is, multiplied by your pressure, which is 100. But that number cannot be more than 12 feet. Now, if you're doing the non-constrained, then you can take, or the equation tells you 1/3 of the depth, and that still cannot exceed 12 feet. So for non-constraint, you can go to 16 or 17 feet or whatever, because you're saying 17 feet multiplied by third, that number is still going to be less than 12. So that's kind of where they differ a little bit. But the bottom line is that as far as the capacity goes, whether it's S1 or S3, which is those are the capacities from the code, where they take the 100 and multiply it by the depth, that cannot be more than 12 feet. I hope this kind of answers it a little bit. But yes, it's all about the capacity, and the capacity has to be kept at the 12 times that pressure, 100 or 200, whatever that pressure that you're using is. You cannot use any more capacity than that, even if you go embedment, I don't know, 40 feet.
Perfect. All right, next question. We generally apply load at the center of the pole. Any insights on it? Applying the load at the center simplifies moment and shear calculations. So um, it sounds like that's in reference to axial load, because eccentric axial load would create moment. You have the option in the embedded pole footing embedded module to apply axial load and to apply moment. So you can kind of decide for yourself whether you want an axial load plus a moment it induces, or if you just want an axial load, or if you just want a pure moment. You have some flexibility on that. As far as how you decide to apply those, it varies widely based on the geometry of the system you're designing and the judgment for how your office tackles those. But you do have the flexibility to do lateral distributed loads, um, lateral concentrated loads, applied moments, and axial loads. Go ahead, Mac, if you had anything to add on that.
No, that's exactly right. If your axial load is applied at an eccentricity, so it's not concentric, then you have a moment component. And if you want to apply that separately as a moment component, you could. If you want to ignore it, you can just put the axial by itself. But you have the ability to add just pure moment directly. And Seth, I want to go back to that question with the 12 foot. If you open ENERCALC and you go inside the pole footing embedded in soil and click on this button right here, that will take you to the help section, that kind of the user manual that shows you everything. This shows you a good write-up of what's going on, and this is kind of when using that 12-foot limit right here. It tells you exactly what the software is doing. So in this case, 24 feet embedment divided by third is 14 feet. 14 feet is more than 12. Therefore, it'll be capped at 12. So that's kind of how ENERCALC goes about it, and that's how we interpret it. So again, that would be a good read for the person who asked the question, just to get a little bit more insight on how we interpret this. And of course, if you have any more questions about this, you can send us an email at support.com or support@enercalc.com.
All right, next question. Would be great if ENERCALC would auto-calculate the self-weight of the pier footing caisson when checking in-bearing pressure for use when checking in-bearing pressures or when using allowable skin friction. So again, just because of the references to end-bearing and skin friction, I do want to reinforce that the process we're talking about here doesn't rise to the level of the kind of geotechnical analysis and soil structure analysis that you need to do actual drilled piers. Because we're doing an embedded pole, it's a slightly different animal. However, there is a place for that end bearing check, and so that would be a feature request if you'd like to see footing self weight implemented. Absolutely feel free to send that over to the support team, support@enercalc.com. And of course, obviously, that would involve adding a field for the density of the whatever is the footing material. It's not always going to be the same material. You know, the user would need control over that. But
Yeah, absolutely. Because you can use this module not just for concrete foundations or concrete footings that are embedded. If you have a wood pole that you're just driving all the way in, that could work too. So that's why when it comes to self-weight calculation, we will have to collect density for that material. And right now, just to reiterate, EnerCalc will take your applied axial load and it will divide it by the area and it will give you the demand. So that's the demand, but it does not do anything with checking that against the capacity. In my example, I did that, the 1500 check or, against the demand. That was just an extra step that we did outside of EnerCalc, but EnerCalc doesn't do it. If that's something that you're interested in, whether it's end bearing or a combination of end bearing and some sort of skin friction, if these are things that you're interested in, then please send us a feature request and we can track that.
all right, next question. Does ACI 318 require steel in the footing? So this is an interesting question, particularly because of the point that Mac just made a moment ago, which is the fact that this check is actually would be valid even for just something like a driven post. So there's nothing about this analysis that presumes you have a large chunk of concrete necessarily. However, if you do have concrete, then you would be subject to checking ACI to make sure whether that's required. I know there are provisions in ACI 318 under certain circumstances that say you're off the hook for temperature and shrinkage minimums and footings. We're not explicitly implementing any rebar checks in this particular module. All right, question from Steve. I have poles that are embedded in a top layer of soil and a bottom layer of rock. Is there any way to accurately evaluate the pole depth? So this module does not have the scope to do any kind of soil layering. The IBC process assumes that you have essentially a uniform profile or a singular bearing layer. So your best option would be to either look at a more in-depth analysis or ignore the rock and use the soil with the IBC pole embedded approach. Mac, did you want to chime in on that one?
Yeah, definitely. I mean, yeah, yeah, this is unfortunate because just ignoring the rock is gonna, um, is gonna be very conservative, especially if if the rock is shallow up enough. So yeah, this is unfortunately it's outside of the scope of this module, and that would be something where we would have to, use a different tool or something where we have to layer the soil and get more geotechnical information and do this in a way that
More of a
accurately
robust
depicts
soil
everything.
structure interaction type
Yes, exactly.
situation.
Yeah, definitely. This is not for that. Our module isn't.
All right. All right. And our last question of the day is load linking available in Revit? And that is definitely a big yes. So the process that Mac walked you guys through today, load linking natively inside EnerCalc, is all a manual process where you can manually associate, hey, take this beam, react it onto this column, so on and so forth. However, if you're working in the Revit environment, you can get access to all of that load linking behavior seamlessly and intuitively just because of the spatial relationships and the physical proximity and connectivity between those elements. So, for example, the calculation that Mac is showing you right now, we've got a series of joists on the roof. We can calculate reaction forces for those joists. We can take reactions from those roof joists and automatically associate them to that girder that holds up the edge of the roof. We can automatically take reaction forces from that girder and transfer them directly into that column. We can do that at a specific eccentricity, all based on Revit parameters and physical spatial geometry. And then we can even take that axial force in the column and transfer it directly to the footing. So that was the long answer to your question. The short answer is yes, you have all of those same capabilities, but it's all seamless and intuitive based on physical proximity rather than having to manually create those relationships on the fly. And feel free to reach out if you have more questions about that.
Yeah, absolutely. And that I just want to add, I don't think I heard you say this, but yeah, you can definitely take all. It's a the reason why we say it's a full gravity load path, here is that because it takes it all the way from your beam or your joist to your columns, all the way to your foundations, and of course. We cover, wood beams, composite, steel composite beams, and stuff like that. So you get a lot more connectivity between the members instead of having to manually link a beam to a column. The column already knows which beams that they're actually linking into it, and it will grab the reactions from them directly. So.
Yeah, and that even includes more interesting gravity framing conditions like transfer post conditions, where you have a transfer girder, transfer post, post lands on a girder, and then that girder lands on a building column, and you can transfer through multiple layers of gravity framing. All right. Well, that was our last question for today. Thank you, everybody, for chiming in with those great questions. Again, if we encouraged you to do so, based on the nature of your question, be sure to reach out to the support team and we can get those questions answered, get those feature requests logged. Mac, do you want to close us out with a teaser for next month with a date and topic for
Yes.
noon office
Well,
hours?
we have a date. Let me go all the way back right here. There you go. All right. Yeah, our next session is going to be June 11th. We have a couple of topics pre-selected that we're still trying to figure out which we want to do. So stay tuned. Probably whenever we send